The third topic in the first week, or in the first chapter, is operations on sets. When we talk about sets, we will often use the so-called logical operators. Or sometimes called quantifiers. We will use two of them. One of them is called the existence quantifier, and there's a special symbol for that. It's the reversed E, again called the existence quantifier. It stands for the words there exists or there are. There exists or there is or there are. And also the generalization quantifier. It's the reverse A letter. The logic is this: E for exists and A for any. Generalization quantifier. Again, this stands for the words for every or for any. For example, we can make the following statement. If, say, A and B are sets, if A and B are sets, then the statement that for every x, x belongs to A, if and only if x belongs to B, another round of parentheses is needed, simply means what? It means that for every element x anywhere in the universe, whenever x is an element of the set A, x is also an element of the set B, and vice versa. Whenever x is an element of the set B, x is also an element of the set A. Because every set is completely determined by its elements, this statement simply means that A and B are equal. Right? This simply means that the set A equals the set B. In fact, we can define equality of sets this way. Sets A and B are called equal. Sets A and B are called equal. Which is written naturally A equals B if I can just copy paste that statement for every x, x is in A, if and only if x is in B. As an example, we can write the negation of this statement. Right? Let's use logical notation to write the statement that two sets are not equal. Right? What does it mean? for two sets, A and B to be not equal. Well, it means, right, A not equal B, call inequality. Remember, that means definition. A not equal to B means that there exists an X such that either X is in A and not in B, or X is in B, but not in A. Note how when you negate a statement, the generalization quantifier changes to existence quantifier. When negating a statement, generalization quantifiers, generalization quantifiers replace existence quantifiers. And vice versa. All right. We can also use logical language to write what's known as inclusion relation. What does it mean to say that one set is a subset of another set? Right? If A and B are sets, by A included in B, that symbol means subset. And what this says is A is a subset of B. Column equality, that means definition. What does it mean? It means that for every X, whenever X is an A, right, it follows that X is in B. And it's easy to visualize, right? If we write our sets as these potatoes, A subset of B means that whenever X is an A, right, it must be necessarily inside B. The condition that A is a subset of B doesn't exclude that A and B are equal. Specifically, when A is a subset of B, but A is not equal to B, we will say that A is a proper subset of B. When A is a subset of B, and A is not equal to B, we say that A is a proper subset of B. All right. Also, using the inclusion relation, inclusion relation. We can write set equality in a different way. Note that two sets are equal if and only if one of them is a subset of the other and vice versa. So A equals B if and only if A is a subset of B and B is a subset of A. So what does it mean to say that A is not a subset of B? Right, the negation to the condition that A is a subset of B is written naturally. A is not a subset of B. And what does it mean? How do we define A not a subset of B? Well, that means there exists at least one X such that X is in A and not in B, which again is easy to visualize. Right? If this is A and say this is B, I can easily find an X which lies entirely in A but lies outside B. Now I'd like to mention again set builder notation, which we talked about already, but let me talk about it again briefly. Let's say M is a set. Let M be a set. And suppose that every element of M, every element X of M, either has or doesn't have some property which we write capital P. So we can distinguish every element of the set M by whether that element has or doesn't have property P. We will write that P of X if X satisfies property P. If X has P, we write P of X. And then we can construct a subset of the set M. We have a tool to construct subsets of the set M. By using set builder notation. We can, for instance, write, give me all elements in M which have property P. Right? Again, that means X in M such that X satisfies property P. One obvious statement here is that M itself can be defined this way. Every subset of M can be defined this way, including M itself. For instance, M could be written as all those X's in M that are in M. It's a trivial statement, X is in M such that X is in M is the set M itself. In particular, this implies that M is a subset of itself. So every set naturally is a subset of itself. In a similar way, we can construct another special subset of the set M. We can select elements of M satisfying a certain property that no element of M can satisfy. Right? For example, we can take P of X to be the condition that X not equal to X. Naturally, no element X of the set M can satisfy this property. Right? So if we consider all those elements in M satisfying property P, which in this case is all those elements in M, such that X is not equal to itself. And of course, this set cannot contain any elements because no element can satisfy the property of not being equal to itself. Any element of the set M must be equal to itself. And if I require that no element be equal to itself, or rather, if I require to select only those elements that are not equal to themselves, it means I select nothing. We select no elements of M. That is given a special name. That is called an empty set. Circle with a bar. Empty set. Contains no elements. An interesting fact is that the empty set is a subset of any set M and of course the empty set is a subset of itself. Again, the empty set is a subset of any set M because it was constructed using the set builder notation from the set M. All right, now I'm going to talk a little bit about basic operations on sets. Operations on sets. Let's say we have two sets, A and B, which are subsets of some bigger set called capital M. A and B are subsets of a set which we call capital M. So I will define the following operations. Union of sets. The union of sets A and B simply means merging of all elements from A and all elements of B. The formal definition is this: A cup, that's the union symbol, colon equality, that's definition, curly braces, because it's a set, refers to all those x's in M such that either x is in A or x is in B. Note that this is not excluding the possibility that X is in both. I don't mean to say that X is either in A but not in B, or in B but not in A. It's perfectly fine if X is in both A and B. Now, to visualize this, we can draw M as a rectangle. Here is set A, here is the set B, and the union is simply anything in A or anything in B. A union B. Right, the next operation is intersection. And I can kind of copy from here, I hope, intersection of two sets the symbol is reversed cup. A intersect B is the set of, or rather the subset of M that consists of those elements of M that are in both A and B. So here, instead of or, I should write and. In terms of the picture, I should change that accordingly. Here is the set A, and here is the set B, and A intersect B is simply the overlapping part of A and B. All right, next operation is difference of sets. Again, I should maybe not copy. Difference. The difference of two sets. Of A and B written A minus B, or set minus B. The formal definition is this. A minus B is defined, column equality, set all those x's in our universe M which are in A and not in B. So if you visualize this, again, this is our universe M. This is A. This is B. So we need the portion of A that's outside B. The portion of A that's outside B, that is what A minus B is. All right, the last operation I'm going to talk about is complement. Also very useful, will be used very frequently. Complement. Unlike the previous operations, this one will require only one argument. So the complement of a set A in M written, well, there are two different notations which are used all the time, either A superindex subscript C or A over bar. That simply is the difference of the universe and our set A. So formally, AC or A bar is M minus A, and that is the set of all those x's in M which are not in A. To visualize this, we can draw a picture similar to the ones we drew before. So this is our universe M. Let's say this is our set A. So we simply want everything outside the set A. That's A, C, or A bar. All right, that's it for the operations on sets.